Hello there, and welcome back to Snoozing Ideas channel. I'm so glad you found your way here tonight. Whether your mind is racing with the day's thoughts, or you're simply seeking a gentle drift into dreams, you've arrived at exactly the right place. Take a deep breath now, and another. Feel your shoulders softening as tension melts away. Tonight, we'll be venturing into one of the universe's most misunderstood wonders, black holes. Though they might sound intense, there's something deeply soothing about these cosmic travelers. These silent guardians of space-time have been patiently spinning for billions of years, teaching us about gravity's gentle embrace and the poetry written in starlight. As you nestle deeper into your pillow, we'll explore the surprisingly peaceful truths about these cosmic phenomena that cradle entire galaxies in their mysterious arms. Let's begin. Black holes begin as stars that reach a beautiful end. When massive stars exhaust their nuclear fuel, they can no longer support themselves against their own immense gravity. The core collapses inward with unstoppable force, compressing to an infinitely dense point, while the outer layers explode as a supernova. This transformation occurs when stars at least 20 times more massive than our Sun complete their life cycle. Not all massive stars become black holes. Some become neutron stars instead, depending on their precise mass and composition. The boundary between these destinies lies hidden in equations still being refined by astronomers. What causes one star to become a neutron star and another a black hole? Perhaps the most profound feature of black holes is how they represent nature's ultimate transformation. Matter crushed beyond recognition, becoming something entirely new. The event horizon marks an invisible boundary between our universe and something else. This spherical threshold surrounds every black hole, defining the point of no return for anything that crosses it. Scientists calculate its size using the black hole's mass. The more massive the black hole, the larger its event horizon. For a black hole with our Sun's mass, this boundary would stretch just under 3 kilometers across. The event horizon isn't a physical surface, but a mathematical boundary in space-time. While we cannot see the event horizon directly, we can observe its effects on surrounding matter. Is there something fundamentally different about space itself at this border? The event horizon stands as a cosmic shoreline, beyond which the familiar physics we understand gives way to something we can only describe mathematically. Light itself cannot escape the grasp of a black hole. Once any particle, wave, or information crosses the event horizon, the escape velocity exceeds the speed of light, 300,000 kilometers per second. Since nothing can travel faster than light according to Einstein's theories, nothing that enters can ever emerge again. This absolute imprisonment makes black holes the most efficient traps in the universe. Computer simulations show how light rays bend increasingly as they approach, until at the event horizon they curve back upon themselves. Black holes create the universe's deepest shadows, regions where even light itself must surrender to gravity's pull. A German physicist solving Einstein's equations first predicted black holes. In 1916, while serving on the Russian front during World War I, Karl Schwarzschild found a solution to Einstein's newly published theory of general relativity. His mathematics described a point where space-time curved infinitely, a singularity surrounded by what we now call the event horizon. Einstein himself initially doubted such objects could physically exist. The mathematical prediction came decades before astronomers had any observational evidence for black holes. The term black hole wasn't even coined until 1967 by American physicist John Wheeler. Science sometimes glimpses the truth through pure mathematics before observation can confirm it. Schwarzschild's discovery, made in the trenches of war, revealed one of the universe's most profound secrets written in equations. At the heart of nearly every large galaxy lurks a supermassive darkness. Astronomers have found evidence that most galaxies, perhaps all of them, contain enormous black holes at their centers. These cosmic anchors can have masses millions or billions of times greater than our Sun. The relationship between these central black holes and their host galaxies appears fundamental. The mass of the black hole correlates strongly with properties of the galaxy surrounding it. This suggests they evolve together, their fates intertwined across cosmic time. How did these enormous objects form in the early universe? Perhaps these silent giants are not merely residents of galaxies, but essential architects in their formation and evolution. Our home galaxy harbors a hidden colossus named after a constellation. At the center of the Milky Way, 26,000 light-years from Earth, resides a supermassive black hole astronomers call Sagittarius A. First detected by radio emissions from its vicinity, this invisible object anchors our entire galaxy of 200 billion stars. Its presence was confirmed by tracking stars that orbit an apparently empty point in space at tremendous speeds. For decades, astronomers watched these stars trace elliptical paths around something massive yet unseen. Could there be something more exotic than a black hole at our galaxy's core? In 2022, the Event Horizon Telescope captured the first direct image of Sagittarius A, revealing the telltale shadow of our galaxy's central engine. A monster with the mass of 4 million suns sits quietly at our galaxy's heart. Sagittarius A, our central black hole, contains an almost unimaginable amount of matter, compressed into a region smaller than our solar system. Despite this enormous mass, it's relatively quiet for a galactic black hole, not currently consuming large amounts of material. Astronomers determined its precise mass by tracking stars that orbit it, particularly one called S2 that completes an orbit in just 16 years. The immense gravitational influence extends for light years in all directions, helping to shape the central bulge of our galaxy. What would happen if we could visit this cosmic giant? Like a silent sovereign, Sagittarius A rules from its throne at the galactic center, its gravitational decree obeyed by countless stars. Black holes don't hunt. They simply wait for matter to cross their paths. Despite their fearsome reputation, black holes don't actively pull in distant objects like cosmic vacuum cleaners. They obey the same laws of gravity as stars or planets. An object must come very close to a black hole to be captured. Otherwise, it will merely orbit, just as Earth orbits the Sun. The misconception of black holes as cosmic predators stems partly from visualizations, showing funnel-shaped distortions of space-time. In reality, objects far from a black hole orbit normally, unaware of its presence. Could we safely orbit a black hole as we do our Sun? Black holes are patient cosmic architects, shaping space around them while matter traces orbital paths, dictated by the curved fabric of space-time. The point of no return requires an actual crossing to claim its prize. Objects near a black hole can still escape its influence if they remain outside the event horizon. A spaceship with sufficient fuel could orbit a black hole and depart safely, just as satellites orbit Earth. This boundary marks where escape velocity equals the speed of light. Cross it, and capture becomes inevitable. Simulations show that from the perspective of distant observers, objects approaching this boundary appear to slow down, freeze, and redden as light struggles against gravitational pull. Time stretches near this cosmic threshold where reality's rules begin to fray. The event horizon stands as a one-way membrane in the cosmic ocean. Matter passing through becomes part of the black hole itself. Time flows differently in gravity's deepest wells. Near a black hole, time itself stretches and slows due to the extreme warping of space-time. This isn't an illusion. It's a fundamental aspect of how gravity affects reality. An observer watching a clock fall toward a black hole would see it tick progressively slower as it approaches the event horizon. For someone falling with that clock, time would seem to pass normally, but they would witness the outside universe speeding up, evolving rapidly before their eyes. 1 hour near the event horizon might correspond to years or centuries for distant observers. What strange awareness might develop at the edge of forever? Like honey dripping from a spoon, time flows with viscous reluctance where gravity reaches its greatest strength. Einstein predicted time's malleable nature decades before we could measure it. The slowing of time near massive objects, gravitational time dilation, emerges directly from Einstein's 1915 theory of general relativity. His equations showed that gravity isn't a force, but the curvature of space-time itself. This revolutionary concept predicted that massive objects would cause time to flow more slowly in their vicinity. The effect is subtle on Earth, but becomes dramatic near black holes, where gravity reaches extreme values. GPS satellites must account for time dilation, or they would accumulate errors of about 10 kilometers per day. How strange that the nature of time itself changes depending on where you stand. Einstein's equations revealed time as a flowing river, running swiftly in some places and barely moving in others. Stars dancing around an invisible partner reveal the presence of darkness. Astronomers detect black holes by observing their gravitational effects on nearby stars and gas. When stars orbit an apparently empty region of space, their movements trace the outline of something massive yet unseen. High-resolution observations of the galactic center show stars whipping around an invisible object at speeds exceeding 25 million kilometers per hour. Their precisely measured orbits allowed scientists to calculate the mass of Sagittarius A with remarkable precision. The black hole itself remains invisible, but its gravitational choreography of nearby stars unmasks its presence. Nature allows us to see the unseeable through the cosmic ballet of stars responding to gravity's silent call. Matter screams in X-rays as it makes its final plunge. Gas, falling toward a black hole, forms a swirling accretion disk that heats to millions of degrees due to compression and friction. This superheated plasma emits intense X-ray radiation before crossing the event horizon. The X-ray emissions often flicker and pulse as chunks of matter spiral inward, creating distinctive patterns that astronomers can measure. These emissions are among the most energetic phenomena in the universe, sometimes outshining entire galaxies of stars. What secrets might be encoded in these final electromagnetic messages? Like the last notes of a cosmic symphony, infalling matter broadcasts its existence in high-energy frequencies before joining the silent collection of mass within the black hole. Astronomers find the invisible by looking for its fiery appetite. The X-ray signatures from matter falling into black holes provide crucial evidence for their existence. Space telescopes like Chandra and XMM Newton detect these high-energy emissions, allowing astronomers to locate black holes that would otherwise remain hidden. The patterns of X-ray fluctuations reveal details about the black hole's mass and spin. Particularly bright X-ray sources often indicate binary systems where a black hole is gradually consuming a companion star. These observations confirmed the existence of black holes decades before we could image their shadows directly. Sometimes we find what we seek not by seeing the thing itself, but by noticing what happens around it. Some black holes are relatively modest, weighing only as much as several suns. Stellar mass black holes form from the collapsed cores of massive stars and typically contain between 3 and 20 times the mass of our Sun. Astronomers have identified dozens of these objects within our galaxy. They're often found in binary systems with ordinary stars, revealing themselves as they pull matter from their companions. The smallest black holes approach the theoretical minimum mass required for gravitational collapse to overcome neutron degeneracy pressure, about 2.2 solar masses. Some scientists speculate that even smaller black holes might exist if formed through exotic mechanisms rather than stellar collapse. Within their compact event horizons, these black holes contain the compressed remains of once brilliant stars. The cosmic weight class between small and supermassive remains mysterious. Intermediate mass black holes, with masses between 100 and 100,000 times that of our Sun, represent a puzzling middle category that has proven difficult to confirm. Theoretical models suggest they might form when many stars collide in dense stellar clusters, or perhaps from the direct collapse of enormous gas clouds in the early universe. Recent gravitational wave detections have provided some evidence for black holes in this mass range. These middleweights could be crucial for understanding how supermassive black holes grow so large so quickly after the Big Bang. Could they be missing evolutionary links? Like gaps in an evolutionary tree, intermediate black holes may represent important but elusive stages in the development of their supermassive cousins. The universe's true leviathans weigh as much as billions of suns combined. Supermassive black holes, found at the centers of galaxies, reach masses that stagger the imagination, millions to billions of solar masses. The formation of these cosmic giants remains incompletely understood. They may have grown by merging with other black holes, by consuming enormous quantities of gas, or perhaps they formed directly from the collapse of massive gas clouds in the early universe. Their growth appears connected to the evolution of their host galaxies in ways astronomers are still unraveling. These enormous objects can influence star formation across thousands of light years. Silently dominating galactic cores, supermassive black holes shape the evolution of entire island universes through their gravitational rule. The current heavyweight champion contains the mass of 40 billion suns. The largest known black hole resides in the galaxy TON 618, containing approximately 40 billion times our Sun's mass. This colossus lies about 10.4 billion light-years from Earth. Its event horizon would span a region larger than our entire solar system. If placed at the center of our galaxy, it would consume much of the inner stellar population. Astronomers detected this giant by measuring the intense radiation from its accretion disk, which outshines the galaxy around it. The existence of such enormous objects raises questions about how they could grow so large in the limited time since the Big Bang. Like ancient mountains eroded by time, these cosmic giants may hold clues to the universe's distant youth. Black holes spin in majestic silence, dragging the fabric of reality with them. Most black holes rotate because they form from stars that were already spinning. Conservation of angular momentum ensures that as a star collapses, it spins faster, like a figure skater pulling in their arms. Some black holes rotate at significant fractions of the speed of light, creating profound effects on nearby spacetime. This rotation stores enormous energy that can theoretically be extracted. Rapidly spinning black holes have different properties than stationary ones, including smaller event horizons for the same mass. Could we someday harness the rotational energy of black holes? Like cosmic gyroscopes, rotating black holes spin endlessly in the dark, their angular momentum a fossil record of their formation. The mathematics of spinning darkness required a different set of equations. Rotating black holes are described by the Kerr metric, a solution to Einstein's field equations, discovered by New Zealand mathematician Roy Kerr in 1963. This mathematical framework accounts for how rotation affects the surrounding spacetime. The Kerr solution revealed that spinning black holes have more complex geometry than non-rotating ones, including regions where spacetime itself is dragged around the black hole. For decades, this remained a theoretical curiosity until astronomical observations confirmed that most black holes indeed rotate. What other mathematical solutions might reveal new aspects of reality? In the silent language of equations, the Kerr metric describes the elegant geometries that emerge when mass, energy, and rotation reach their ultimate expression. Space and time themselves are pulled into a cosmic whirlpool by rotation. A spinning black hole creates a remarkable effect called frame dragging, where it pulls the fabric of spacetime around with it, like honey being stirred. Any object near a rotating black hole will be forced to move in the direction of the black hole's spin, even if no other forces act upon it. This isn't a traditional force, but a fundamental warping of the structure of spacetime itself. The faster the black hole spins, the more pronounced this effect becomes. Near the event horizon, frame dragging becomes so extreme that nothing can remain stationary. Space itself flows like a river, carrying all within it on a journey around the central abyss. Physicists named the cosmic carousel after the scientists who predicted it. Frame dragging is also called the Lenz-Thirring effect, after Austrian physicists Joseph Lenz and Hans Thirring, who predicted it in 1918. This subtle phenomenon occurs around any rotating mass, including Earth, but becomes dramatically stronger near black holes. NASA's Gravity Probe B satellite confirmed frame dragging around Earth in 2011, measuring how our planet's rotation slightly drags space-time around with it. The effect is billions of times stronger near rotating black holes, creating a space-time whirlpool that nothing can resist. Have we fully mapped all the ways rotation affects reality? Like invisible currents in a cosmic ocean, frame dragging reveals how rotation shapes the hidden flow of space-time itself. Between the event horizon and ordinary space lies a region where space itself rotates. Around spinning black holes forms an unusual region called the ergosphere, a flattened sphere where space rotates so rapidly that nothing can remain stationary. Unlike the event horizon, objects can still escape from the ergosphere if they move with sufficient energy. This region extends outward from the event horizon, reaching farthest along the black hole's equator. The faster the black hole spins, the larger this region becomes. The ergosphere represents a transition zone between normal space and the event horizon, a place where rotation dominates reality. Here, in this twilight region, space itself participates in an eternal dance around the central axis of the black hole. Within the spinning ergosphere, freedom of movement faces a curious restriction. Any object entering the ergosphere must begin moving in the direction of the black hole's rotation, regardless of its initial trajectory. This isn't a traditional force, but a fundamental limitation on possible motion within this region. While objects here can still escape the black hole, they cannot remain stationary or move against the flow of space-time. Theoretical models suggest this effect could allow energy extraction from the black hole through a process called the Penrose process. Would a spacecraft entering this region feel these limitations? Like leaves caught in a whirlpool, objects in the ergosphere must surrender to the rotational flow of space-time before they can navigate within or beyond it. A gentle quantum glow may emanate from what we thought was absolute darkness. In 1974, Stephen Hawking predicted that black holes should emit a faint radiation due to quantum effects near their event horizons. This Hawking radiation arises when virtual particle pairs form spontaneously near the horizon, a phenomenon permitted by quantum mechanics. When one particle falls in and the other escapes, the black hole effectively loses mass. This theoretical radiation would be extremely faint for large black holes, making it currently impossible to detect directly. The prediction revolutionized our understanding of black holes, suggesting they aren't completely black after all. Like whispers from the edge of existence, Hawking radiation represents the subtle conversation between quantum mechanics and gravity. The eternal might not be so eternal after all. According to quantum mechanics, black holes can gradually lose mass through Hawking radiation. As they emit this faint radiation, they slowly evaporate, a process that contradicted the classical view that black holes could only grow or remain stable. This quantum leakage means that given enough time, all black holes would eventually disappear completely. The energy of the emitted particles comes from the black hole's mass, following Einstein's famous equation, E and mc2. The process accelerates as the black hole shrinks, culminating in a final burst of energy. Could the universe's darkest objects ultimately fade away? In the quantum realm, even black holes may be transient features in the cosmic landscape, their seemingly infinite darkness subject to the inexorable laws of evaporation. The cosmic patience required for large black holes to vanish exceeds imagination. For black holes with significant mass, the evaporation process through Hawking radiation occurs at an extraordinarily slow pace. The larger the black hole, the colder its radiation, and the slower it evaporates. A black hole with the mass of our Sun would take approximately 1067 years to completely evaporate. A time span trillions of times longer than the current age of the universe. During most of this time, the radiation would be so faint as to be undetectable by any conceivable instrument. What processes in nature require such vast timescales? The evaporation of large black holes represents perhaps the longest predictable process in the universe, a cosmic countdown measured in quintillions of years. A black hole weighing as much as our Sun would outlive almost everything else. At an estimated 1067 years to evaporate completely, a solar mass black hole would persist long after all stars have burned out and all planets have disintegrated. This time span is so vast that it exceeds our ability to truly comprehend it. It's roughly 1057 times the current age of the universe. During this immense period, the black hole would radiate at a temperature of only about 1/10,000,000th of a degree above absolute zero. The universe itself might fundamentally change before such a black hole could disappear. In the far, far future, black holes may become the last structured objects in an otherwise empty cosmos, slowly releasing the energy locked within them. The universe's largest black holes will be the last objects to fade from existence. Supermassive black holes, with their enormous masses, evaporate at rates so slow that their lifetimes stretch beyond comprehension. A black hole, with the mass of 1,000,000,000 suns, would take approximately 10 or 100 years to evaporate completely, a number so large it dwarfs even the time required for quantum tunneling of matter into iron. These objects would outlast everything else in the universe, persisting through the dark era when no stars shine and even protons may have decayed. Their final moments would release tremendous energy into an otherwise empty cosmos. Like the last candles in a darkened universe, supermassive black holes may provide the final flickering light before eternal darkness. Smaller black holes burn hotter in a cosmic paradox of temperature. According to Hawking's equations, a black hole's temperature is inversely proportional to its mass. The less massive a black hole, the hotter its radiation. This creates the counterintuitive situation where smaller black holes are actually hotter than larger ones. A black hole with the mass of Mount Everest would radiate at roughly the temperature of our Sun, while one with the mass of our Sun would be colder than the cosmic microwave background. This relationship means that as black holes lose mass through evaporation, they grow progressively hotter, accelerating the evaporation process. The mathematics of this relationship emerges from the fundamental constants of nature themselves. In the quantum realm, size and temperature dance in perfect inverse harmony. The universe's tiniest black holes would shine with brilliant intensity. Extremely low-mass black holes would emit radiation at tremendously high temperatures. A black hole with the mass of a small asteroid would glow with radiation hotter than the core of the most massive stars. One with the mass of a mountain would shine brighter than a supernova as it approached the final stages of evaporation. These micro-black holes would have incredibly short lifespans compared to their larger cousins, potentially evaporating completely in seconds or years rather than eons. No such small black holes have ever been detected, suggesting they either don't exist or have already evaporated. The smaller the dragon, the hotter its breath. Tiny black holes would burn briefly, but with unmatched ferocity before vanishing from the cosmos. The early moments after creation may have forged black holes of many sizes. Primordial black holes could have formed in the extreme density fluctuations present during the first fraction of a second after the Big Bang. Unlike stellar black holes, which form from collapsed stars, these ancient objects could have masses ranging from microscopic to thousands of solar masses. Different formation times would produce different characteristic masses, earlier formation allowing for smaller black holes due to the universe's greater density. The existence of primordial black holes remains theoretical, as none have been definitively detected despite several observational campaigns. Could the universe's first seconds have created objects that still exist today? Like fossils from cosmic infancy, primordial black holes would carry information about conditions in the newborn universe. The cosmic attic may contain black holes of every conceivable size. If primordial black holes exist, they could span an enormous range of masses, from the weight of a mountain to thousands of solar masses. The smallest would have long since evaporated through Hawking radiation, while intermediate-sized ones might still exist today. These ancient objects would have formed before any stars or galaxies, making them among the oldest structures in the universe. Their distribution and abundance would provide crucial information about conditions in the early universe and the physics of extreme densities. What other relics from cosmic dawn might still exist? Primordial black holes would represent nature's earliest experiments with gravity's ultimate expression, preserved across cosmic time. The universe's missing mass might hide in primordial darkness. Some cosmologists have proposed that primordial black holes could constitute a portion of dark matter, the mysterious substance that makes up approximately 85% of the universe's mass. If they exist in sufficient numbers, Primordial black holes with masses between that of a small asteroid and a small star could account for some or all of this missing mass. These objects would be extremely difficult to detect directly, as they wouldn't interact with light except through gravitational effects. Recent gravitational wave detections have renewed interest in this possibility. Might we be surrounded by ancient black holes, too small to see? Like shadows cast by the Big Bang itself, primordial black holes could silently fill the cosmic voids, their gravity shaping the universe while remaining hidden. Black holes can dance in pairs, spiraling ever closer while sending ripples through space-time. Binary black hole systems consist of two black holes orbiting their common center of mass. As they orbit, these pairs lose energy by emitting gravitational waves, ripples in space-time that travel outward at the speed of light. This energy loss causes the black holes to spiral closer together in an accelerating cosmic dance that ultimately ends in merger. The final moments of this process release enormous energy, briefly outshining all the stars in the visible universe, not as light, but as gravitational waves. Astronomers estimate our galaxy contains thousands of such binary systems in various stages of their evolutionary dance. Each pair traces a gravitational waltz that will end in perfect union as two become one. Ripples in the fabric of space-time confirmed a century-old prediction. In September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time, confirming a major prediction of Einstein's general relativity. These waves, detected as incredibly subtle distortions in space-time, originated from the merger of two black holes approximately 1.3 billion light-years away. The signal lasted only 0.2 seconds, but provided definitive evidence for both gravitational waves and black holes. LIGO's detectors measured changes in distance smaller than 1/10,000th the diameter of a proton. How remarkable that such cosmic cataclysms can be detected through their gentle ripples in space-time. Like listening to the universe's heartbeat, gravitational wave astronomy opened a new sense with which to perceive the cosmos. A cosmic collision unimaginably distant reached Earth as the faintest whisper. The first detected gravitational wave event, designated GW15914, originated from two black holes spiraling together and merging 1.3 billion light-years from Earth. These black holes, with masses of 29 and 36 times our Sun respectively, combine to form a single black hole of 62 solar masses. The missing 3 solar masses converted to energy in the form of gravitational waves, briefly radiating more power than all the stars in the observable universe combined. Yet when these waves reached Earth, they distorted space-time by less than the width of an atomic nucleus. The signal arrived at Earth after traveling across 1 billion light-years of space, carrying information from a time before complex life existed on our planet. From unimaginable violence comes the gentlest of cosmic messages. The cosmic dancers that created history's first detected gravitational waves were unremarkable in size. The black holes that produced the first detected gravitational wave signal had masses of approximately 29 and 36 times that of our Sun. Modest by cosmic standards, yet much larger than most stellar remnants in our galaxy. Their merger formed a single black hole with about 62 solar masses, with the equivalent of 3 solar masses converted to gravitational wave energy during the final coalescence. This detection revealed a population of black holes more massive than previously observed in our galaxy, suggesting different formation environments or mechanisms. Since this historic detection, Dozens more black hole mergers have been observed, mapping out the population of these invisible objects. Each detection adds a new point of light to our map of the previously invisible cosmic darkness. 3 suns vanished in a whisper that crossed 1 billion years. When black holes merge, mass transforms into pure energy, gravitational waves rippling outward through the fabric of space-time. In the first detected merger, 3 solar masses, 3 stars' worth of matter, simply ceased to exist as matter, becoming instead a tremor in reality itself. This energy release, though enormous, created no light, no heat, no sound, only the gentlest stretching and squeezing of space as it passed. Einstein's equations predicted this conversion long before we could detect it. That matter and energy are different expressions of the same essence remains one of physics' most profound insights. Somewhere in the vastness, black holes continue their silent dance, turning mass into whispers that travel endlessly through the dark. Ripples in the cosmic ocean travel at light's own pace. Gravitational waves move through the universe at precisely 299,792,458 meters per second, the cosmic speed limit shared by light. Unlike sound waves needing air or water, these space-time ripples require no medium, flowing through perfect vacuum and solid matter alike. They carry messages about cosmic collisions across billions of years, largely undisturbed by the matter they pass through. When 2 black holes spiral together in the distant universe, the news of their union races outward in expanding spheres, a fundamental vibration that speaks of massive bodies and curved space. These waves represent gravity itself in motion, the geometry of space and time breathing in and out as the message passes. As gravity's message passes, space breathes in and out. When gravitational waves flow through a region of space-time, they momentarily stretch and compress the very fabric of reality. Distances between objects grow slightly longer in one direction, while simultaneously shortening in the perpendicular direction. This rhythmic alteration, though incredibly subtle by the time waves reach Earth, represents actual physical distortion of space itself. LIGO's detectors measured changes smaller than the width of a proton to sense these cosmic tremors. That space itself can flex, and wave contradicts our intuitive sense of rigid reality. Yet here, in the quiet breathing of distances, we glimpse the living, dynamic nature of what we once thought was merely empty void. Humanity's first glimpse of darkness came from an unexpected glow. In 1971, astronomers studying a strange X-ray source in the constellation Cygnus realized they were witnessing something extraordinary. The invisible object pulled gas from a companion star, heating it to millions of degrees as it spiraled inward, creating a beacon visible across thousands of light years. Calculations revealed an object too dense to be a neutron star, the first confirmed black hole. This discovery transformed black holes from mathematical curiosities to physical realities. For centuries they existed only in equations. Now they had addresses in our sky. How strange that these ultimate embodiments of darkness announced themselves through light. Their presence revealed not by what they are, but by what happens around their edges. A darkness 15 times more massive than our sun spins through the Swan. Cygnus X1, our first discovered black hole, contains approximately 15 solar masses compressed into a region smaller than a city. This stellar remnant was once the core of a blue supergiant star that lived fast and died young, collapsing under its own weight. Now it orbits a massive blue companion star, their celestial dance a study in extremes, one visible across thousands of light years, the other fundamentally unseeable. For half a century, astronomers have studied this system, refining our understanding of its properties and behavior. In the darkness between the stars, this invisible object continues its eternal orbit, a hidden weight bending the path of light and matter alike. 6,000 years of light separate us from our nearest known darkness. Cygnus X1 resides approximately 6,000 light-years from Earth, a distance so vast that the light we observe today began its journey when humans were just beginning to create written language. The X-rays we detect carry information from a different era of human history. While astronomers have since discovered black holes both closer and far more distant, this first confirmed specimen remains among our most studied neighbors. What ancient eyes might have gazed upward at Cygnus, never knowing that among its stars drifted one of the universe's most extreme objects? In the span of a single human lifetime, our understanding reached across millennia to grasp what had always been there. Black holes are not always solitary wanderers through the cosmic night. Many drift through space with stellar companions, locked in mutual orbit by gravity's embrace. These binary systems form when a massive star collapses while already paired with another star, or through later gravitational capture. The resulting dance can last billions of years. The visible star, tracing an ellipse around an apparent emptiness. These cosmic pairs provide astronomers with rare opportunities to study black holes, as their gravitational influence on companions can be precisely measured. How remarkable that in the emptiness between galaxies, pairs of objects, one blazing with thermonuclear fire, the other an absence of light, might orbit one another in perfect gravitational harmony for longer than Earth has existed. The black void slowly consumes its shining partner. In binary systems, a black hole's gravity pulls streams of gas from its stellar companion in a process astronomers call accretion. This stellar material doesn't fall directly inward, but follows a spiral path dictated by conservation of angular momentum. Some stars lose mass equivalent to several Earths each year to their dark companions. This cosmic feeding process can continue for millions of years until the donor star is stripped to its core or expands to engulf the black hole entirely. There is a strange intimacy in this astronomical exchange, matter from one object slowly becoming part of another. Like ancient deities slowly consuming their children, these cosmic predators patiently feed across eons. Around the darkness swirls a disk of light, matter's final dance before oblivion. Stellar material pulled from companion stars doesn't immediately cross the event horizon, but forms a flattened disk of orbiting gas. This accretion disk develops as particles collide, losing vertical momentum while conserving angular momentum. The innermost regions orbit faster than outer regions, creating friction that heats the gas to extreme temperatures. These structures can span millions of kilometers, yet be thinner than Earth relative to their diameter. Accretion disks represent the universe's most efficient energy conversion mechanisms, transforming gravitational potential energy into radiation with greater efficiency than nuclear fusion. In these swirling patterns of doomed matter, nature reveals its most beautiful arrangement: spirals, the shape of both galaxies and water, down a drain. The final moments of matter generate heat that defies imagination. As gas spirals through an accretion disk, friction and compression heat it to millions or even tens of millions of degrees, far hotter than the core of our sun. At these temperatures, matter breaks down into plasma, emitting intense X-ray and gamma radiation detectable across vast cosmic distances. This superheated matter glows with the energy of its own demise, broadcasting its fate across the universe. The mathematics describing these temperatures emerged naturally from Einstein's equations decades before observation confirmed them. Through this extraordinary heat, the invisible announces itself. Black holes, the darkest objects in existence, ironically creating some of the universe's brightest beacons. From cosmic whirlpools erupt fountains stretching across light years. Some accreting black holes launch tremendous jets of particles perpendicular to their accretion disks, extending far beyond their host galaxies. These relativistic jets form when magnetic fields around the black hole channel some infalling matter away at nearly light speed. The process involves complex interactions between gravity, magnetism, and rotational energy that astronomers still work to fully understand. These cosmic fountains can influence star formation and galactic evolution across enormous distances. How curious that objects defined by their inescapable gravity also create the most powerful outflows in the universe. Like nature's ultimate contradiction, black holes both consume and create, gathering matter while launching some of it back into the cosmos in magnificent displays of energy. The cosmic plumes stretch farther than entire galaxies are wide. Relativistic jets from black holes can extend for thousands or even millions of light years. Structures so vast, they dwarf their entire host galaxies. These enormous features remain collimated over these distances, maintaining their narrow shape against the tendency to disperse. Some jets from supermassive black holes reach scales where their outer edges lie in regions of space that have never received light or matter from their origin point through any other path. That such coherent structures can maintain their integrity across intergalactic distances reveals fundamental properties about the nature of space itself. Like cosmic rivers flowing through the emptiness, these jets connect distant regions of the universe in a single continuous stream. Within these cosmic rivers, subatomic particles race at nature's speed limit. The material in relativistic jets travels at velocities exceeding 99% of the speed of light. So fast that time itself flows measurably slower for these particles than for the universe around them. At these speeds, particles live longer from our perspective than they would at rest, and their mass increases according to Einstein's equations. These extreme conditions create unique astrophysical laboratories for testing fundamental physics. That macroscopic structures spanning light years can maintain such velocities demonstrates the extraordinary efficiency of nature's acceleration mechanisms. Along these invisible highways, protons and electrons journey between galaxies, carrying with them the signature of their violent origins near a black hole's edge. The universe's brightest beacons are powered by its darkest objects. Quasars, quasi-stellar radio sources, are active galactic nuclei, where supermassive black holes consume matter at extraordinary rates. These cosmic engines can outshine their entire host galaxies, emitting energy across the electromagnetic spectrum. First discovered as star-like radio sources in the 1960s, their true nature remained mysterious until spectroscopic measurements revealed their extreme distances and therefore luminosities. That objects defined by their inability to emit light could generate the universe's most powerful sustained energy sources seemed paradoxical. Yet, in this apparent contradiction lies a profound truth about nature's efficiency. The steeper the gravitational well, the more energy can be extracted as matter falls toward it. Single objects that outshine hundreds of billions of stars. The most luminous quasars emit energy equivalent to thousands of Milky Way galaxies, all from regions smaller than our solar system. This extraordinary output comes from the gravitational potential energy of matter falling toward supermassive black holes, converted to radiation with up to 40% efficiency. By comparison, nuclear fusion in stars converts less than 1% of rest mass to energy. These cosmic lighthouses can be seen across the observable universe, their light traveling for billions of years before reaching our telescopes. That such concentrated brilliance can emerge from the darkest objects in existence represents one of astronomy's most beautiful paradoxes. In the silent depths of intergalactic space, these beacons announce the presence of cosmic engines operating at the limits of physical law. Light that begins its journey when Earth is young finally reaches our telescopes. The most distant quasars we observe emitted their light more than 13 billion years ago, when the universe was less than 1 billion years old. This ancient light carries information about conditions in the early cosmos and poses challenging questions about how such massive black holes formed so quickly after the Big Bang. As this light traveled toward Earth, the universe expanded, stretching its wavelengths toward the red end of the spectrum. When astronomers decode this redshift, they read not just distance, but time, windows into cosmic history. How remarkable that we can observe light that began its journey before our solar system existed, carrying messages from a universe still in its infancy. Through distant beacons, we read the universe's earliest chapters. Quasars serve as cosmic archaeological sites, allowing astronomers to study conditions in the early universe. Their light passes through intergalactic hydrogen on its journey to Earth, creating absorption patterns that reveal the distribution and state of matter billions of years ago. The presence of massive black holes in the infant universe constrains theories of structure formation and galaxy evolution. That such extreme objects existed when the universe was less than 1 billion years old suggests either extraordinarily rapid growth or alternative formation mechanisms for the first black holes. Like cosmic time capsules, these distant points of light preserve information about an era otherwise lost to us, the adolescence of our universe. At some galactic centers, darkness feeds with terrible efficiency. Active galactic nuclei contain supermassive black holes that actively consume surrounding gas, dust, and even stars. These feeding phases can last millions of years, generating tremendous energy through accretion disks, jets, and intense radiation that affects the entire host galaxy. The material falling inward forms structures governed by magnetohydrodynamics, the complex interaction of gravity, gas pressure, and magnetic fields. These active phases represent transient periods in a galaxy's life, punctuating longer dormant intervals. What cosmic triggers awaken these sleeping giants remains an area of active research. Like heartbeats in galactic lifespans, these feeding events mark rhythms in the long evolution of these island universes. Most cosmic leviathans currently rest in quiet hibernation. The majority of supermassive black holes in the present-day universe are dormant, not actively accreting significant amounts of matter. These sleeping giants still exert their gravitational influence, but don't produce the brilliant displays of their active counterparts. Our own galaxy's central black hole, Sagittarius A, is currently in such a quiescent state, though evidence suggests it was more active in the recent astronomical past. The cycling between active and dormant phases may influence galactic evolution through feedback processes. What dreams might fill these periods of cosmic quietude? Like ancient dragons sleeping beneath galactic mountains, these enormous objects wait through the slow drift of stars, perhaps to awaken again when new matter ventures too close. When galaxies embrace, their central darknesses begin a slow dance toward union. Galaxy mergers bring supermassive black holes into the same system, beginning a process that may eventually lead to their coalescence. This cosmic ballet occurs in distinct stages spanning billions of years. First, the black holes sink toward the merged galaxy's center through dynamical friction. Then, they form a binary system, orbiting their common center of mass while gradually losing energy. Finally, they spiral together until gravitational waves carry away the last orbital energy, resulting in merger. This process shapes the population of supermassive black holes we observe today. Through violence comes creation. Cosmic collisions ultimately birth new configurations of stars, gas, and the invisible weights at their centers. Cosmic islands regularly merge across the vast ocean of time. Galaxy collisions, once thought catastrophic and rare, are now understood as common events that drive cosmic evolution. A typical galaxy like our Milky Way has experienced multiple merger events throughout its history, each reshaping its structure and stellar populations. These slow-motion collisions unfold over hundreds of millions of years as galaxies first approach, pass through each other, and eventually settle into new combined forms. Stars rarely collide during these events due to the vast spaces between them, but gas clouds intersect and compress, triggering bursts of new star formation. The universe writes its history through these gentle cataclysms, gradual restructurings of matter across timescales that defy human comprehension. Our galaxy's future includes an inevitable collision with our largest neighbor. In approximately 4.5 billion years, the Andromeda Galaxy will merge with our Milky Way in a cosmic dance already underway. Currently approaching at about 110 kilometers per second, Andromeda's gravitational embrace will transform both spiral galaxies into a single elliptical galaxy astronomers have whimsically named Milkomeda. The collision will trigger new star formation as gas clouds interact, while the supermassive black holes at each galaxy's center begin their own slow journey toward merger. By this time, our sun will have evolved into a red giant, having already rendered Earth uninhabitable. The night skies of whatever world still host observers will witness a transformation billions of years in the making. After galaxies merge, their central darknesses engage in a final gravitational embrace. When the Milky Way and Andromeda galaxies combine billions of years from now, their supermassive black holes will begin a journey toward eventual union. Sagittarius AI and its counterpart in Andromeda will first sink toward the center of the newly formed elliptical galaxy through interactions with surrounding stars. Over hundreds of millions of years, they will form a binary system, orbiting each other while gradually losing energy through gravitational interactions. In the final moments, they will spiral rapidly together, releasing enormous gravitational wave energy. This future cosmic event will not be witnessed by human eyes. Like all perfect unions, the final merger will transform both objects into something new, a single entity bearing the combined mass of its progenitors. Near a black hole's edge, matter stretches like cosmic taffy. Tidal forces, the difference in gravitational pull between the near and far sides of an object, become extreme close to a black hole. An astronaut falling feet first would experience stronger gravity at their feet than their head, creating an ever-increasing stretch. Theoretical physics describes this process mathematically, showing how an object would extend into a thin strand as it approaches the event horizon. The vivid term spaghettification entered scientific literature to describe this fatal stretching. That gravity, usually experienced as a gentle, uniform force, can become so dramatically differential near black holes reveals the true nature of this force. Not a pull, but a curvature in the fabric of space-time itself. The uneven embrace of extreme gravity pulls objects apart. Spaghettification occurs because gravitational force follows an inverse square law. Doubling your distance from a mass quarters the gravitational attraction. Near black holes, this gradient becomes incredibly steep. An object 1 meter long falling toward a stellar mass black hole might experience millions of times stronger gravity at its leading edge compared to its trailing edge when close to the event horizon. This differential force overwhelms the electromagnetic bonds holding matter together, causing stretching along the radial axis and compression along perpendicular axes. The mathematics describing this process emerged naturally from Einstein's field equations. In the extreme warping of space near a black hole, we find the true nature of gravity revealed, not as a force, but as geometry given expression, a whimsical name for the universe's most extreme form of destruction. Astrophysicist Martin Rees coined the term spaghettification in his 1977 book to describe the stretching of objects near black holes. This vivid terminology entered scientific literature, making a complex physical process accessible through familiar imagery. While playful, the term precisely captures the physics involved. Matter stretched into thin strands by tidal gravitational forces. That scientists use pasta analogies to describe phenomena at the edge of known physics speaks to our need to connect the exotic to the familiar. In the borderlands between comprehensible physics and the truly strange, language itself stretches to accommodate concepts that defy everyday experience, reaching for metaphors that build bridges to the unimaginable. For cosmic giants, the point of stretching lies hidden behind the veil, around supermassive black holes. The radius where spaghettification occurs actually falls inside the event horizon. This means a person could cross the point of no return before experiencing extreme tidal forces. This counterintuitive fact emerges from the mathematics. Larger black holes have proportionally larger event horizons, but less extreme gravitational gradients at their boundaries. For a black hole with millions of solar masses, an astronaut could cross the horizon relatively intact, only experiencing fatal stretching well after passing into the region from which escape is impossible. How strange that the larger the abyss, the gentler its initial embrace. The true violence awaits inside, hidden from the external universe by the cosmic censorship of the event horizon itself. The boundary between the known and unknown might feel remarkably ordinary as you cross it. For sufficiently massive black holes, an observer crossing the event horizon would notice nothing special at that precise moment. The laws of physics dictate that from the falling observer's perspective, the horizon isn't a physical surface, but a mathematical boundary. Local space-time appears normal, with extreme effects only becoming apparent as the center is approached. Only when looking outward would the observer notice something unusual, the visible universe compressed into an increasingly small patch of sky above them. This smooth crossing emerges naturally from general relativity. In the mathematics of black holes lies a profound insight, that the most significant boundaries in nature may pass without notice, their importance apparent only in retrospect. The ultimate threshold may pass beneath your feet with no fanfare. For a person falling into a supermassive black hole, the event horizon crossing would lack any dramatic physical sensation. No alarm sounds, no barrier breaks, no sudden change in the local environment marks this cosmic point of no return. The enormous scale of these objects creates a gradual gravitational gradient rather than a sharp boundary. Only later, as the center is approached, would tidal forces become noticeable and eventually overwhelming. That such a profound transition, crossing from a region where return is possible to one where it is not, could occur without sensory indication, speaks to the subtle nature of space-time itself. Perhaps the most significant thresholds in existence are those we cross without knowing, their importance clear only when reflection becomes impossible. Black holes remember only 3 things about their past. According to the no-hair theorem in theoretical physics, once matter crosses the event horizon, all its detailed properties vanish, except for 3 fundamental parameters: mass, electric charge, and angular momentum. All other information, the hair, is lost to the outside universe. A black hole formed from collapsing stars would be indistinguishable from one formed from collapsing light or exotic matter, provided these 3 quantities match. This mathematical result emerged from solutions to Einstein's field equations in the 1960s and 1970s. That objects of such complexity could be reduced to just 3 numbers challenges our intuitions about physical information. Like cosmic amnesiacs, black holes forget almost everything about their formation, retaining only these fundamental quantities as they drift through the cosmic night. 3 numbers fully describe the universe's most complex objects. Mass tells us the black hole's gravitational influence, charge indicates its electromagnetic properties, and angular momentum describes its rotation. According to the mathematics of general relativity, these 3 parameters completely characterize a black hole. All others are either derivable from these or irrelevant to external observers. This extraordinary simplification stands in stark contrast to other astronomical objects that require numerous parameters to describe. The discovery of this principle by physicists including Werner Israel, Brandon Carter, and Stephen Hawking fundamentally changed our understanding of these objects. That such extraordinarily complex entities can be fully described by so few parameters reveals a profound simplicity underlying apparent complexity, a theme that recurs throughout theoretical physics. The ultimate cosmic amnesia erases everything else about what falls in. When matter crosses the event horizon, all information about its composition, structure, and quantum states appears to vanish from the universe, leaving only mass, charge, and spin as measurable properties. A black hole formed from collapsed stars would be identical to one formed from light or exotic matter, provided these 3 quantities match. This information loss applies to all other distinguishing characteristics, whether the infalling matter was hydrogen or iron, ordered or disordered, simple or complex. That the universe would allow such apparent information erasure troubled physicists deeply. In the silent darkness beyond the event horizon, the rich complexity of matter seems to dissolve into mathematical simplicity, leaving only shadows of its former attributes. A profound contradiction emerges between 2 fundamental theories at the horizon's edge. The information paradox arises from the conflict between general relativity, which suggests information is lost in black holes, and quantum mechanics, which holds that information cannot be destroyed. If information truly disappears when matter falls into a black hole, fundamental principles of quantum physics would be violated. This tension between our two most successful physical theories has driven theoretical physics forward for decades. Some of the greatest minds in physics, including Stephen Hawking, Leonard Susskind, and Juan Maldacena, have grappled with this problem. That two theories could be so individually successful, yet fundamentally incompatible at their intersection, points to deeper principles still waiting to be discovered. For nearly half a century, physicists have wrestled with a cosmic riddle of vanishing information. Since Hawking's 1976 paper, highlighting the conflict between information conservation in quantum mechanics and information loss in black holes, this paradox has generated numerous proposed resolutions. Some suggest information is encoded in the Hawking radiation through subtle quantum correlations. Others propose it remains stored at or near the event horizon. More exotic solutions involve higher dimensions, holographic principles, or modifications to quantum mechanics itself. The paradox represents a profound boundary in our understanding of nature. Like ancient philosophers, confronting the limits of reason, modern physicists stand at the edge where our best theories fail to provide satisfying answers, pointing toward deeper principles that may unify our understanding of reality's most fundamental aspects. The universe may preserve its memories through whispers we cannot yet detect. Recent theoretical work suggests information falling into black holes may be preserved in subtle quantum correlations within Hawking radiation. Though each emitted particle appears random, patterns across all particles emitted throughout a black hole's lifetime might encode complete information about everything that fell in. Alternative theories propose information might be stored in complex quantum structures at the event horizon itself, or in subtle distortions of spacetime that persist after the black hole evaporates. These potential solutions require extensions to our current understanding of physics. Like a message written in invisible ink, the information consumed by black holes may remain present in the cosmos, written in a language of quantum correlations that our current scientific vocabulary cannot yet fully articulate. Through the looking glass may lie the temporal reverse of darkness. In theoretical physics, white holes represent time-reversed black holes, regions that cannot be entered, but from which matter and energy can escape. Einstein's equations permit these solutions mathematically, though no evidence suggests they exist in nature. While black holes inevitably draw matter inward across their event horizons, white holes would expel material that, from our perspective, could only have existed inside them eternally. Some theories suggest black holes might transform into white holes through quantum processes, resolving the information paradox by eventually releasing everything they consumed. That the same mathematical framework describing cosmic sinkholes also predicts their opposite reminds us how physics often reveals symmetries hidden beyond intuition. The universe's greatest givers may exist only in equations. White holes would function as cosmic fountains, regions from which matter and energy emerge, but into which nothing can fall. Unlike black holes, which have substantial observational evidence, white holes remain entirely theoretical. Their existence would violate the second law of thermodynamics unless they represented the time reversal of black hole formation and evaporation. Some speculative theories suggest the Big Bang itself might have been a white hole, expelling the contents of a previous universe. Others propose that black holes might eventually transform into white holes after reaching maximum entropy. These mathematical possibilities emerge naturally from Einstein's field equations. In the fertile ground between established physics and speculative mathematics, white holes represent intriguing cosmic possibilities that may never be realized in our universe. the cosmic bookends to black holes, remain conspicuously absent from our observations. Despite extensive astronomical surveys, no object matching the theoretical properties of white holes has ever been detected. Their absence poses interesting constraints on theoretical physics, suggesting either that the mathematics permitting them represents a solution not realized in nature, or that they manifest in ways we haven't recognized. Some theories propose they might exist only briefly as transitional states during black hole evolution, making detection extraordinarily unlikely. Others suggest they might exist in other universes or dimensions connected to our own through black holes. That nature appears to favor cosmic drains, while avoiding cosmic fountains represents an intriguing asymmetry in the physics of space-time. Like mythical creatures from scientific equations, white holes inhabit the borderlands between mathematical possibility and physical reality. We have always dreamed of shortcuts through the vast cosmic ocean. Wormholes, theoretical tunnels through the fabric of space-time, might connect distant regions of the universe, offering passages beyond the limitations of light speed. The mathematics describing these cosmic corridors emerges naturally from Einstein's field equations, the same equations that predicted black holes decades before we found them. Though we've never observed a wormhole, they live in our scientific imagination as bridges across the unbridgeable. Perhaps we're drawn to the possibility of wormholes because they echo something we understand intuitively, that connection matters, that distance can sometimes be an illusion, that the universe may hold secret passages we have yet to discover. In our dreams of wormholes, we recognize our deep desire to touch the distant, to make far become near. The equations that describe our universe whisper of hidden tunnels. Some solutions to Einstein's field equations suggest black holes could connect to white holes through space-time tunnels, theoretical structures we call wormholes. These mathematical bridges might link distant regions of our universe or perhaps connect to other universes entirely. What exists as possibility in our equations might exist as reality somewhere beyond our current reach. We seek these connections in our mathematics just as we seek them in our lives. Pathways that bring the separate together, bridges across what seems unbridgeable. Though we may never find a wormhole in our cosmic neighborhood, the very possibility reminds us that reality often exceeds our imagination, that what seems disconnected may share hidden unity. The cosmic shortcuts we imagine would require matter, unlike anything we've found. Traversable wormholes, stable enough for anything to pass through them, would need exotic matter with negative energy density to hold open their delicate throats against collapse. This strange material would effectively push outward against gravity rather than attract. While quantum physics allows negative energy to exist fleetingly in small amounts, the quantities needed for wormholes remain beyond our reach. Yet we continue exploring these possibilities, calculating what might be possible at the edges of physics. Isn't this pursuit itself a reflection of who we are? Beings who search for connections, who imagine what might lie beyond current limitations. Even in our mathematical dreams, we reach for ways to bridge the unbridgeable distances between stars. Our telescopes have yet to find doorways in the fabric of space, despite extensive searches of the night sky. Astronomers have found no observational evidence for wormholes, no unexplained gravitational lensing, no unusual patterns in starlight that might reveal these cosmic passages. Yet their absence from our observations doesn't diminish their place in our scientific imagination, in our stories, or in our ongoing exploration of physics. We continue searching because the universe has surprised us before, revealing wonders initially thought impossible. Perhaps the real magic of wormholes lies not in whether we'll find them, but in how they inspire us to keep looking up, to keep wondering what might be possible. In our search for cosmic connections, we reveal our own nature. Curious beings who never stop asking what lies beyond. Light itself can dance in perfect circles around cosmic darkness. At precisely 1.5 times the Schwarzschild radius of a black hole exists a special region called the photon sphere, where light can orbit in perfect circles around the central mass. These photons trace the boundary between paths that escape to infinity and those that inevitably fall inward. Though such orbits are unstable, theoretically, light could circle a black hole many times before drifting away or spiraling in. What a view it would be, to witness the universe reflected again and again, stars appearing as perfect rings as their light circles this cosmic drain. In these perfect orbits of light, we glimpse something profound about balance. How even at the edge of ultimate darkness, perfect motion is still possible. There exists a sphere of light caught between escape and capture. The photon sphere surrounds every black hole at exactly 1.5 times the event horizon radius for a non-rotating black hole. This mathematical boundary emerges naturally from Einstein's equations, not as an arbitrary distance, but as a fundamental property of curved space-time. Here, gravity bends light into circular paths, creating a region where photons can orbit like planets around a star, though their orbits remain unstable. This exact distance, this 1.5 factor, appears again and again in our calculations, a universal ratio that would be the same anywhere in the cosmos. Don't we all seek such perfect balances in our lives? Places where competing forces reach equilibrium, where we are neither falling in nor flying away, but moving in harmony with what surrounds us. Imagine light frozen in perpetual orbit, never escaping, never falling in. At the photon sphere, light rays can travel in perfect circles around a black hole, caught in the precise balance between the pull of gravity and light's natural tendency to travel in straight lines. From this special distance, a photon directed perfectly tangential to the black hole will neither escape to infinity nor fall into the event horizon, but circle forever, at least in theory. In reality, the slightest deviation sends these photons spiraling either outward or inward. We rarely find such perfect balance in our lives, moments where we are neither moving away from nor drawn too close to what matters. Yet in these fleeting equilibriums, we sometimes find our truest perspective, seeing everything around us with new clarity. Even the smallest particles need to maintain their distance to find stability. Matter with mass cannot orbit a black hole stably any closer than 3 times the Schwarzschild radius, a region called the innermost stable circular orbit. Beyond mathematics, this boundary represents a fundamental transition in how objects can move in the presence of extreme gravity. Inside this limit, all paths lead inevitably inward, regardless of speed or direction. This invisible boundary exists around every black hole in the universe, a universal property of how mass, energy, and space-time interact. Don't we recognize similar boundaries in our own lives? Invisible lines, where stability gives way to inevitable change, where maintaining distance becomes necessary for survival. Sometimes, wisdom lies in knowing the orbits we can sustain, and those we cannot. There comes a point near cosmic darkness where stability itself dissolves. Inside the innermost stable circular orbit, no matter how fast an object moves, all paths lead inward toward the black hole's center. Even particles traveling at nearly the speed of light cannot maintain circular paths. the curvature of space-time becomes too severe. This isn't just an interesting fact. It's a profound statement about the nature of space itself near extreme gravity. The very concept of a stable orbit simply ceases to exist in this region. We've all felt moments where balance seems impossible, where no amount of effort can maintain equilibrium. Yet, even in these inevitable transitions, there is a kind of peace in surrendering to natural law, in acknowledging the boundaries of what's possible. The invisible boundary that defines absolute separation bears the name of its discoverer. The Schwarzschild radius marks where space becomes so curved that even light cannot escape, creating the event horizon of a non-rotating black hole. Carl Schwarzschild calculated this boundary in 1916 while serving on the Russian front during World War I, finding beauty in equations while surrounded by human conflict. This radius scales perfectly with mass. Double the black hole's mass, and you double this critical distance. There's something deeply moving about this proportionality, this perfect scaling between mass and the size of its shadow in the universe. Perhaps we all cast shadows proportional to our presence, influencing the world around us in ways that extend beyond our physical form. If our sun were to collapse completely, its absence would span just 6 kilometers across. A black hole with our sun's mass would have a Schwarzschild radius of approximately 3 kilometers, its event horizon fitting comfortably within the bounds of a small town. This modest size belies the sun's enormous mass, showing how incredibly dense black holes truly are. The mathematics tell us this radius equals 2.95 kilometers multiplied by the mass in solar units, a simple formula connecting size to mass for every non-rotating black hole in the cosmos. Isn't there comfort in such universal relationships? In knowing that certain proportions remain constant throughout the universe, that the same physical laws that govern distant cosmic darkness also govern the world outside your window. Our entire planet, if compressed beyond imagination, would become a marble-sized darkness. Earth's mass, if concentrated to the density of a black hole, would create an event horizon just 9 millimeters across, smaller than a cherry. Yet this tiny dark sphere would still contain our planet's entire mass, still exert the same gravitational pull on distant objects. The contrast between our living world, with its oceans, mountains, forests, and countless life forms, and this tiny sphere of compressed space-time reminds us how much reality depends on arrangement, not just substance. We are not just matter, but matter beautifully arranged, not just mass, but mass given room to express itself through complexity and relationship. In the space between particles lies the possibility of everything we cherish. Light itself grows tired climbing away from intense gravity. When light escapes a gravitational field, it loses energy, shifting toward longer, redder wavelengths, a phenomenon called gravitational redshift. Unlike the Doppler effect, this shift happens even when the source isn't moving relative to the observer. It's space itself that stretches the light. The deeper the gravitational well, the more pronounced this effect becomes. We witness similar transformations in our lives when we overcome challenges, emerging changed by the effort of the climb, carrying with us evidence of where we've been. Haven't you felt this yourself? How experiences that require the most energy to escape often leave their mark on us, subtly changing how we appear to those who've remained at a distance. Messages from the edge of darkness arrive, transformed by their journey. Light escaping from near a black hole's event horizon reaches distant observers significantly redshifted, its wavelengths stretched by the intense gravitational field it traversed. This isn't merely a color change. It represents actual energy lost as photons work against gravity. For light originating very close to the event horizon, this redshift becomes so extreme that the once vibrant emissions shift beyond visibility, their energy diluted almost to nothing. We recognize this pattern in our own communications, how messages from our deepest places often arrive altered, their meanings stretched and transformed by the journey. Perhaps true understanding requires accounting for the wells we've all had to climb from, the invisible shifts our words undergo on their way to being heard. The closer light originates to the edge of no return, the more profoundly its voice changes. Just outside a black hole's event horizon, gravitational redshift becomes nearly infinite. Light waves are stretched beyond recognition, their frequencies approaching zero. A flashlight waved by an astronaut falling toward the horizon would appear to distant observers to glow increasingly red, then infrared, then radio, its messages taking longer and longer to arrive until they essentially freeze at the horizon itself. We all know this feeling, how our most intense experiences often leave us struggling for words, how language itself seems to stretch and slow when trying to convey what lies at our personal horizons. Some journeys transform not just the traveler, but the very messages they send back about where they've been. The universe's greatest monsters grow through both patience and violence. Supermassive black holes increase their mass through two primary means: steadily consuming gas, dust, and stars that venture too close, and through cosmic collisions with other black holes during galaxy mergers. These growth mechanisms mirror rhythms we recognize in our own world: the slow accumulation of small changes and the transformative power of momentous events. From masses initially perhaps just hundreds of times our Sun, these objects grow over billions of years to contain billions of solar masses. Isn't there something reassuring in this cosmic patience? Even the most powerful entities in our universe required time to become what they are, growing not instantly but through processes that span ages, teaching us that significant growth rarely happens overnight. The cosmic giants may have begun as humble seeds in the universe's springtime. Supermassive black holes likely formed from smaller seed black holes in the early universe, perhaps remnants of the first massive stars or direct collapses of primordial gas clouds. These seeds found themselves in privileged positions, often at the centers of forming galaxies, where material was abundant for growth. Like all origins, theirs remains partly hidden from us, their beginnings obscured by time and distance. Yet we can trace their likely paths through models and simulations, seeing reflections of familiar patterns. How being in the right place with the right conditions allows for extraordinary development. Perhaps our own potential similarly depends on finding our center, our place of greatest nourishment, where growth becomes not just possible, but inevitable. Some cosmic leviathans achieved greatness when the universe was still in its youth. Astronomers have discovered supermassive black holes exceeding 1 billion solar masses when the universe was less than 1 billion years old. Giants that somehow grew to enormous proportions in a cosmic blink. Their precocious development challenges our understanding, suggesting either extraordinarily rapid growth or alternative formation pathways we haven't yet discovered. Don't we see this same phenomenon in human development? Some souls seem to arrive fully formed, achieving depths of understanding or creativity that others take decades to approach. The universe reminds us that growth doesn't always follow predictable timelines. Sometimes extraordinary development happens with startling speed, breaking all our models of what should be possible. We're still learning how cosmic giants grew so quickly in the universe's adolescence. The rapid growth of supermassive black holes in the early universe presents a genuine puzzle. Traditional accretion processes seem too slow to explain their development in the available time. Astronomers explore various solutions. Perhaps they formed from direct collapse of massive gas clouds, bypassing the stellar phase entirely. Maybe they grew through rapid mergers in the dense early universe, or possibly they accreted matter at rates exceeding theoretical limits. This continuing mystery reminds us how much we still have to learn about cosmic evolution. Isn't there comfort in unsolved questions? In knowing that even with our advanced instruments and mathematics, the universe still holds mysteries that keep us searching, wondering, and imagining new possibilities beyond current understanding. Nearby, stellar remnants offer miniature versions of the universe's most powerful engines. Microquasars, systems where stellar mass black holes actively pull matter from companion stars, produce scaled-down versions of the jets and accretion processes seen in distant quasars. Though millions of times less massive than their supermassive counterparts, these local laboratories allow astronomers to witness similar physics unfolding in real time rather than over millennia. We recognize this pattern of the small reflecting the large throughout nature. How drops of water can contain the same fluid dynamics as oceans, how families might mirror societies. Perhaps there's wisdom in this scaling, in recognizing that fundamental processes often remain similar across vastly different magnitudes. By understanding what's near, we glimpse what happens in realms too distant or massive to observe directly. The cosmic small teaches us about the cosmic large. Microquasars in our galaxy provide crucial laboratories for studying how black holes generate powerful jets, streams of particles traveling at near light speeds. Because changes in stellar mass black holes happen thousands of times faster than in their supermassive cousins, astronomers can observe processes unfold over weeks rather than millennia. This cosmic scaling allows us to study universal processes regardless of size, the same physical laws working across scales spanning factors of millions. How reassuring to discover such continuity in our universe, to find that studying what's accessible can genuinely illuminate what's distant. Perhaps this is true in human experience as well, that by deeply understanding our immediate relationships, we gain insight into broader social patterns that might otherwise remain abstractions. Humanity united to capture what was thought impossible, the image of absence itself. In April 2019, the Event Horizon Telescope collaboration revealed the first direct image of a black hole, specifically the supermassive black hole at the center of galaxy M87. This achievement required converting our entire planet into a single virtual telescope, combining radio observatories across continents to achieve unprecedented resolution. Over 200 scientists from 20 countries worked together for years, overcoming technical challenges once thought insurmountable. The resulting image, a glowing orange ring surrounding a dark center, represents not just a scientific milestone, but a testament to human cooperation. When we set aside differences and combine our perspectives, we can see what was previously invisible, turning impossibility into an image that will forever change how we visualize the cosmos. We've seen the unseeable together. The first black hole image, released in 2019, showed the supermassive black hole at the center of galaxy M87, a giant elliptical galaxy 55 million light-years from Earth. This single image represented the culmination of decades of theoretical work, technological development, and international collaboration. 8 radio telescopes on 4 continents synchronized their observations, collecting petabytes of data that required 2 years of processing to transform into the iconic image that made headlines worldwide. The orange ring revealed precisely what Einstein's equations had predicted a century earlier: a dark shadow surrounded by light, bent by extreme gravity. Isn't there something deeply moving about this achievement? That through shared purpose and cooperation, humanity could reveal something fundamental about the universe that no individual could possibly see alone. The dark giant in that famous golden ring outweighs 6 billion suns. The supermassive black hole at M87's center contains approximately 6.5 billion solar masses, enough to fill our entire solar system with darkness. This extraordinary object drives 2 massive jets of particles, stretching thousands of light-years into space, influencing galaxy evolution across cosmic distances. The sheer scale of this object challenges comprehension. A single invisible entity, with the mass of billions of stars concentrated in a region smaller than our solar system. Yet for all its enormity, it follows the same physical laws as much smaller black holes. There's something strangely comforting in this consistency, that the rules governing reality remain unchanged from human scale to cosmic scale, that the universe maintains its elegant simplicity even at its most extreme. The universe painted its own portrait with light bent around absence. The first black hole image showed not the black hole itself, but its effect on surrounding light, a bright asymmetric ring formed by superheated gas and bent light paths. This luminous circle surrounds a dark central region called the shadow, about 2.6 times larger than the event horizon itself, due to how gravity bends light's path. What looks simple to casual observers represents extraordinary complexity, the combined effect of gravitational lensing, relativistic beaming, and the black hole's rotation. The image's brighter bottom portion reveals the black hole's spin direction, gas moving toward us, appearing brighter due to relativistic effects. In this portrait of darkness surrounded by light, we witness the universe's fundamental duality, how absence shapes presence, how emptiness defines fullness. The dark heart of that golden ring isn't just emptiness, it's a shadow cast by light's absence. What we see as the black central region in M87's image isn't the event horizon itself, but a larger shadow, the result of light paths so curved by gravity that they miss the telescope array entirely. This shadow appears approximately 2.6 times larger than the actual event horizon for a non-rotating black hole. The distinction matters. We're not directly seeing the boundary of no return, but rather the region where photons are deflected away from our line of sight. There's poetry in this realization that even when capturing an image of cosmic darkness, we're still seeing it through its effect on light. Perhaps this mirrors our own understanding of profound concepts, grasping them not directly, but through the shadows they cast on what we can perceive. Einstein's century-old equations predicted exactly what we eventually saw. The size and shape of M87's black hole shadow matched predictions from general relativity with remarkable precision, confirmation of a theory developed when radio telescopes didn't yet exist. This agreement between theory and observation represents one of science's greatest validations. Equations written with pencil and paper correctly describing an object 55 million light-years away, containing billions of solar masses. The shadow's measured diameter differed by less than 10% from theoretical predictions, an extraordinary confirmation across cosmic scales. Doesn't this success story remind us of our collective potential? That human imagination and reasoning can reach across space and time, accurately describing what exists far beyond our direct experience. connecting our minds to the fundamental nature of reality itself. We've now seen the face of our galaxy's central darkness. In May 2022, the Event Horizon Telescope revealed its second direct image of a black hole, Sagittarius A, the supermassive black hole at our Milky Way's center. Though millions of times closer than M87, our galaxy's black hole presented greater imaging challenges due to its smaller size and the rapidly changing gas flows around it. The resulting image, another glowing ring around darkness, connects us directly to the invisible object anchoring our galactic home. There's something profound in finally seeing what's been hiding in our cosmic backyard, the object around which our entire galaxy slowly turns. This achievement doesn't just advance science. It deepens our relationship with our galactic home, making the abstract concrete, turning mathematical theory into something we can literally see. Earth itself became one unified instrument to capture cosmic shadows. Both black hole images required synchronizing radio telescopes across our planet, from Hawaii to Spain, from the South Pole to Arizona, creating a virtual telescope approximately the size of Earth. Atomic clocks at each location ensured perfect timing, as massive hard drives recorded petabytes of data that were physically transported to central processing facilities. This planet-scale collaboration overcame not just technical challenges, but geopolitical ones, uniting scientists across borders, languages, and cultures toward a shared goal of seeing the unseeable. Perhaps this represents our highest potential, not just the technical achievement, but our capacity to work as one across traditional divisions. When humanity aligns its efforts, even the shadows at the centers of galaxies cannot remain hidden from our collective gaze. The shadows reveal whether Einstein's vision of gravity holds true at the extreme. Black hole images provide direct tests of general relativity under conditions impossible to replicate on Earth, around objects millions or billions of times more massive than our Sun, where space-time curvature reaches its maximum. The precise shape and size of these shadows confirm Einstein's century-old predictions with remarkable accuracy, validating our fundamental understanding of gravity, where it matters most. Alternative theories of gravity must now conform to these shadow measurements or be abandoned. Isn't there wonder in this connection between theory and observation? That human thought, through mathematics, could accurately describe phenomena so distant and extreme that we're only now developing technology capable of seeing them. Our minds somehow touched cosmic truth long before our instruments could confirm it. Between the small and the supermassive lies a mysterious middle realm we're still struggling to find. Intermediate mass black holes, weighing between 100 and 100,000 solar masses, remain largely theoretical, with only a handful of candidate objects identified. These missing middle black holes should exist according to our understanding of cosmic evolution, possibly forming in dense star clusters, or as stepping stones in the growth of supermassive black holes. Their elusiveness represents a genuine gap in our cosmic census. Don't we recognize this pattern in many fields of knowledge? The extremes often reveal themselves first, while the connecting territory, the middle ground, that might explain how one transforms into the other, remains hidden longest. Perhaps these intermediate objects will eventually help us understand not just what exists at cosmic extremes, but how those extremes relate to one another. The universe's middle children might form through cosmic collisions or special nurseries. Intermediate mass black holes could develop when massive stars merge in dense star clusters, or through repeated mergers of smaller black holes in these stellar nurseries. Alternatively, They might form directly from the collapse of extraordinarily massive gas clouds in the early universe. Their scarcity in our observations might reflect their transient nature. Perhaps they grow quickly into supermassive black holes when conditions allow. The ongoing search for these objects reminds us that nature doesn't always provide convenient examples of every possibility. Some stages of cosmic evolution may be brief, rare, or hidden from our current methods of observation. Yet these missing pieces often hold the keys to our deeper understanding, connecting what we can easily see with what remains mysterious. The universe's subtle ripples may reveal the dance of middleweight darkness. Gravitational waves, ripples in space-time detected since 2015, offer a promising new avenue for discovering intermediate mass black holes through their mergers. Unlike electromagnetic observations, which depend on black holes actively consuming matter, gravitational waves emerge whenever massive objects spiral together, whether visible or not. Several gravitational wave events have hinted at black holes in this intermediate range, though conclusive evidence remains elusive. This new way of sensing the cosmos, feeling its vibrations rather than seeing its light, may finally reveal this missing population. Isn't this how understanding often develops? When conventional approaches reach their limits, entirely new perspectives can illuminate what was previously hidden, revealing not just new objects, but new categories of existence. Physics contemplates a cosmic nightmare. Singularities exposed to the universe. Naked singularities, infinitely dense points of space-time curvature not hidden behind event horizons, represent a troubling theoretical possibility in general relativity. Unlike black holes, where the singularity remains safely concealed from the outside universe, naked singularities would expose this infinite density to direct observation and interaction. The equations permit such objects under certain conditions, yet most physicists believe they cannot exist in nature. What does it say about our universe that it seems to hide its most extreme regions behind horizons of no return? Perhaps there's wisdom in this cosmic censorship. Some boundaries that shouldn't be crossed. Some infinities that should remain veiled. Some aspects of reality too fundamental to be exposed to casual observation. The universe may protect us from its most extreme mathematics. The cosmic censorship hypothesis, proposed by Roger Penrose in 1969, suggests that the universe prevents naked singularities from forming. All true singularities must be hidden behind event horizons. This principle isn't directly proven, but represents a widely accepted conjecture among theoretical physicists. If true, it means the universe maintains a kind of propriety, never allowing regions of infinite space-time curvature to be directly observable. There's something almost poetic about this protective censorship, as if reality itself maintains certain boundaries between what can and cannot be directly experienced. Perhaps this reflects a deeper principle, that while mathematics can describe infinities, nature itself may place limits on what physical processes can actually manifest, preserving a kind of cosmic order. The universe may keep its most extreme regions modestly hidden behind veils of darkness. According to the cosmic censorship hypothesis, all true singularities in nature must remain clothed, concealed behind event horizons that prevent any information about their exact nature from reaching external observers. This principle isn't just mathematical fastidiousness, it preserves the predictability of physics in our universe. If true singularities could be observed directly, the laws of physics would break down in observable regions of space-time. The universe's apparent tendency to hide these extreme regions speaks to a kind of natural order. Don't we recognize similar patterns in our own lives? How certain boundaries and horizons protect us from overwhelming intensity. How some knowledge comes only when we're prepared to receive it. How some mysteries, perhaps, should remain veiled. In higher dimensions, darkness might take forms we can barely imagine. Theoretical physics explores how black holes might behave in universes with extra spatial dimensions beyond our familiar 3. String theory and other frameworks suggest such dimensions might exist, curled up at scales too small to observe directly. In these higher dimensional models, black holes could exhibit properties impossible in our 3-dimensional space, including different shapes, stability characteristics, and radiation signatures. While speculative, these mathematical explorations extend our understanding beyond immediate observation. Isn't there something wonderful about this reaching beyond? That even confined to our 3-dimensional experience, our minds can explore the geometry of what might exist beyond our perceptual limitations, finding consistent mathematics that connects what we know to what we can only imagine. Mathematicians and physicists explore shadow realms beyond our dimensional experience. String theory and related approaches investigate black holes in higher dimensions, universes with additional spatial directions beyond length, width, and height. These theoretical objects would follow different rules than their 3-dimensional counterparts, potentially exhibiting exotic properties like non-spherical event horizons or different evaporation patterns. Though we cannot directly observe extra dimensions, their mathematical consistency provides valuable insights into quantum gravity, the elusive theory uniting quantum mechanics and general relativity. These explorations remind us that reality may be richer than our direct perception suggests, that our 3-dimensional experience might be just one manifestation of a deeper, multidimensional existence. Perhaps the limitations we perceive are not fundamental to reality, but only to our particular vantage point within it. Particle colliders could theoretically create the universe's tiniest black holes. If certain extra-dimensional theories are correct, high-energy particle accelerators might produce microscopic black holes weighing less than a grain of sand. These quantum-scale objects would evaporate almost instantly through Hawking radiation, leaving distinctive energy signatures in particle detectors. Despite concerns raised in popular media, such mini black holes pose no danger. Their gravitational influence would extend less than an atomic nucleus, and their near-instantaneous evaporation prevents them from consuming additional matter. No evidence for their creation has been found in accelerator experiments thus far. There's reassurance in this ongoing dialogue between theory and experiment, each speculation subjected to empirical testing, our understanding refined through both imagination and verification. Our most powerful machines have searched for tiny darkness, but found none. Despite reaching energies where some theories predicted microscopic black hole formation might occur, particle accelerators like the Large Hadron Collider have found no evidence of these quantum-scale objects. This absence places constraints on certain extra-dimensional theories, helping physicists refine their understanding of how gravity might unite with quantum mechanics. Science progresses through both discovery and non-discovery, finding where reality says yes and where it says no. Each experimental null result narrows the field of possibilities, guiding theorists toward more promising avenues. Isn't there wisdom in this methodical approach? In testing even our most elegant theories against reality, in being willing to discard beautiful ideas when observation doesn't support them, in letting nature itself guide our understanding rather than imposing our preferences upon it. Black holes may be the universe's most perfect record keepers. When matter falls into a black hole, its entropy, a measure of microscopic disorder and information content, becomes encoded on the event horizon, increasing its surface area. This relationship, formalized in the second law of thermodynamics for black holes, suggests these objects maintain a perfect accounting of everything that enters them. The total entropy of black holes may constitute the majority of the universe's entropy budget, making them not just cosmic objects, but fundamental components in the universe's information structure. There's something profound in this realization that what appears to be emptiness actually represents the universe's most complete repository of information. Perhaps in our own lives, what seems like absence sometimes holds the deepest record of what has been. A beautiful equation connects the darkness at the heart of galaxies to the heat in your morning coffee. The Bekenstein-Hawking formula relates a black hole's entropy to its surface area. Specifically, its entropy equals 1/4 of the event horizon area, measured in Planck units. This elegant relationship connects gravity, quantum mechanics, and thermodynamics in a single equation, suggesting deeper unity between these seemingly separate domains of physics. That black holes, objects defined by gravity, obey laws of thermodynamics normally applied to ordinary matter, reveals fundamental connections between disparate areas of physics. Isn't this what we seek in our understanding of everything? To find the threads that connect what seems unrelated, to discover that underneath apparent differences lie profound symmetries and relationships that unify our experience of the world. The marriage of gravity and heat may lead us to the universe's deepest secrets. The connection between black hole physics and thermodynamics represents one of the most promising avenues toward a theory of quantum gravity, the elusive framework that would unite general relativity with quantum mechanics. This relationship suggests space-time itself might have an atomic structure, with event horizon area quantized in discrete units, like the energy levels in an atom. What began as a curious parallel between gravitational and thermal systems has blossomed into a profound insight about the nature of space, time, and information. Perhaps the universe's most fundamental truths lie not within any single theory, but at the intersections between them, where gravity meets heat, where the cosmic meets the quantum, where mathematics reveals unexpected harmonies across seemingly unrelated domains of physical reality. As our journey through the cosmic shadows comes to a close, the event horizon of sleep draws near. We've ventured from the theoretical passages of wormholes to the circular dance of photons, from the mathematics of singularities to the first breathtaking images captured by telescopes spanning our planet. Black holes, these silent archivists of space and time, have shared their secrets with us tonight. You exist in a universe where such marvels are real. The same physics that governs these cosmic behemoths also cradles you here on Earth. As you drift toward sleep, remember that somewhere in the vastness above, light traces perfect orbits around invisible giants, and the fabric of space-time curves in silent geometry. The universe's most profound mysteries continue their patient existence while you rest. The cosmic darkness holds no fear, only wonder, just as sleep welcomes you into its peaceful embrace. Your consciousness may dim like light approaching an event horizon, but morning will return, bringing new discoveries. If you find yourself still awake in this quiet moment, perhaps another episode awaits to guide you toward dreams. Our channel has more cosmic lullabies to share. But for now, as the stars wheel silently overhead, I wish you peaceful sleep beneath this vast and beautiful universe. Good night.